Hi everyone, this is the third and probably fourth page of the Chapter 6 exam review for Algebra 2A. Starting here with problem number 16. Number 16 deals with half-life. So before I jump in here, I want to just kind of remind you how half-life works in general. And I wouldn't try to memorize this as like a separate formula. What you should recognize this as is a type of exponential function. So exponential functions always look like this: a times b to the power of x, where a is like an initial value and b is a growth factor. Really, back here on this page, and I'm not sure if you're watching this video, if you watched the previous page, but these were all types of exponential functions. So this was an exponential function where your growth factor was e, right? This is an exponential function where this whole parenthesis piece is like your growth factor. It's your b value. So there's your a, here's your b, and then there's your exponent. So you've been doing exponential functions, but just as a general setup, this is what they look like. So when we're dealing with half-life, we start out with a still being our initial value. Okay, so this is for half-life specifically. The growth factor for half-life is always going to be a 1/2, okay? And then in the exponent, if I just put an x up there, what that's going to do is that's going to make your value cut in half every single year if you put a number of years in for x. But typically, or maybe it's not years, maybe it's minutes or days or however your half-life is being measured, x is the number of minutes or days or hours or whatever your unit of time is. If you want to slow that down, if you want to put that into chunks, so for example, I think in this first example, we've got a half-life of 13 years. What we're going to do is we're going to take that x and divide it by 13, because what that's doing is that's taking your number of years and grouping it into groups of 13 and then saying how many groups of 13 do we have? That's the number of times we need to cut in half. So this is going to be kind of our general setup here. And again, just to remind you that this 13 came from the half-life that was given to us in the problem. So looking at number 16 here, we have a sample of 50 grams, we have 100 years. So 50, that's our A value. Our X is going to be our 100 years. So we are going to set this up as Y equals 50 times 1/2 to the power of 100 divided by 13. So again, what we're really doing there is we're saying how many groups of 13 are there in 100. That's the number of times we need to cut this 50 in half. But we can just type that into the calculator in one shot. So 50, 1/2. And then again, in this calculator, you're going to need parentheses. But we'll end up with 0.24 grams remaining. Okay, this next one, suppose a sample has been decaying for 30 years and currently 2.2 grams remain. I think that's 2.2, or maybe 22. Yeah, I guess I'll run with 22. Okay, so technically what's happening here is the 22 is like our Y value, and we're solving for our A value. But there's another way you could think about this. We could think about this with the 22 grams being my initial value. And then what we want to do is run the clock backwards 30 years. We want to say we have 22 grams right now. If we run backwards 30 years, how much would have been there initially? So to go backwards, we're going to use a mathematical time machine called a negative sign. And we're going to say that our t, I guess it's not t here, I've been using x. So for our x value, we're going to say negative 30 because we want to go back in time, okay? So we could write this as 22 times 1/2 to the power of negative 30 over 13. And what that's going to do is that's going to take us back in time 30 years. So I'm expecting this number to come out larger than 22. And I ended up with 108.9 grams, which makes sense to me. You could have done it the other way. So you could have put the 22 here for Y, and then put a regular 30 in here for x, because you would be running time forward in that way, and then you could have solved for a, what you would end up doing is calculating this piece of the function and then dividing to get the a by itself. That division is really the same thing as using a negative exponent, so that's why it works either way. Okay, we have a sample of unknown mass, so we do not know what a is, but we just want to know how long will it take, so we're trying to find x for 20% of the material to decay. Remember that if you are losing 20%, that means you want 80% remaining. I'm going to kind of approach this one the same way I did back here. When I said if I want it to be worth 30%, I'm going to set it equal to 0.3 and really treat the initial value like a 1. That's the same thing I'm going to do here, is I could come up with any combination of numbers where, this number is 20%, or I'm sorry, 80%. This number is 80% of what I started with. That's what I'm looking for, is how could I get from one value to another where this is 80% of what I started with. The easiest way to do that would be with a 1 here, because then I don't have to do anything with it, and a 0.8 over here. So I'm going to say 0.8 equals, my a value is really like a 1, which I don't care about. And then I'm going to go 1/2 to the power of x over 13, and I'm trying to solve for x. Okay, x in the exponent, that means we're using a log. And I guess you could use a natural log here. Usually I only use natural logs if it's with e, but you could use any type of log that your calculator could do here. So now my function looks like log of 0.8 equals x over 13, that's my exponent, times log of 1/2. I'm going to divide by that log of 1/2. So I'm going to go log 0.8 divided by log of 1/2. And I get 0.32. Oops. But remember, that still equals x over 13. So now what I want to do is multiply by 13 on both sides. So I divided the logs first, but now I'm going to take that number and multiply by 13. And I end up with 4.19 years. So if I took any mass, let's maybe say I started with 100 grams, and I want to do a half-life, so 1/2, and then to the power of, I'm going to go 4.19 divided by 13. What you should find is that 100 grams dropped down to 79.97, which is awfully close to 80, right? So 100 dropped down to 80. That's what we're looking for, right? To lose 20%, so 80% would be remaining. So that would just be a way to verify that your answer is correct. Okay, 17. This question is much easier than it looks. It says rewrite this expression without logarithms. And what I want you to notice is that you've got logs on both sides of this thing. When you're in that situation where you've got logs on both sides, really this is your goal. Your goal is to get it to say log of something equals log of something else. Because if you can get it to look like that, then what we know is these two somethings must be equal to each other. And we can just write it as something equals something. We can kind of leave the logs off of there. I want to caution you, when I do that, it's really just because I know that I'm allowed to have logs on both sides and then the two pieces will be equivalent to each other. It's not that I'm like dividing by the log or canceling out the logs in any way. It's just I know that if I do something to one side and it's equal to doing that same something to the other side, these two values must have been the same to begin with, okay? The reason I'm pointing that out is sometimes I'll see people in this original expression just go through and say, oh, knock out the log, knock out the log, knock out the log. You don't want to do that. You can't do that until you're down to this point where you've got log equals log. So what I want to do is I want to condense this. I want to put this left side together so it's just a single log. So it's just written as one log. That actually goes back to, if you go back to the first page, like the very first question that we did. I'm going to put these numbers out in front, the 2 and the 3, back up as exponents here. And then I'm seeing subtraction here. So when I write this as one giant log, it's going to be with division of the x and the y. So I'm going to have x squared divided by y to the third. Now let's do the same thing over on the right side. I'm going to move this 1/5 back up and make it an exponent. So I'm going to have log of z to the 1/5 power. So now what I can say, and again, I'm going to be very careful not to say that I'm ditching the logs in any way, but this thing must equal this thing. So the expression that I can write is x squared over y cubed must equal z to the 1/5 power. That's how I would answer this question. Okay. This says to evaluate without a calculator. I'm going to be a good role model here and not use a calculator on these. But just remember, you will have a calculator for the entire exam. So if any one of these is difficult for you, I encourage you to go back and look at, which problem number was it here? How we did number 3 back on the first page. Sorry, I know you can't see that on the screen, but number 3, we did log base 2 of 12, and we did it using a calculator. You could use that same method for any of these. So remember, when I ask you to evaluate a log, what I'm really looking for is an exponent. So this question is saying 2 to the power of what equals 128. I guess I'm kind of relying on you to know your powers of 2 pretty well there. That's probably a little larger than I should probably ask you to do without a calculator. But let's see, 2 to the 5th power is 32. So 2 to the 6th power would be 64. So 2 to the 7th power would be double that, so that'd be 128. So here I would say that this answer is 7, because 2 to the power of 7 makes 128. This one is a common log that's a base 10, okay? And this 0.001 place value-wise, that's tenths, hundredths, thousandths. So this is really saying 10 to what power makes 1 over 1,000, because that 1 is in the thousandth spot. So I know it's going to be a negative number, because that's how I get this flip thing to happen with the 1 on top. And then 10 to what power makes 1,000? That would be the third power. So my answer there is going to be -3. By the way, that's a common log, so we could check it in our calculator. Log of 0.001 is in fact -3. Okay. So this one is saying 3 to what power makes 1 over 27. This is going to be really similar to the last one we did. I know it's going to be negative because I have this 1 over number, right? That's going to give me a negative number is how I get a fraction to show up like that. And then 3 to what power makes 27? That's a power of 3. Actually, it's going to be exactly the same as the last one. Also -3. Okay, so this one wants to know a to what power is equivalent to the 4th root of a cubed. So let's think about this and how we would write this using an exponent. This is a to the 3rd power and then a 4th root of that. Remember, a 4th root is really like a power of 1/4. So if we were to put this back together as an exponent, it would be 3 over 4. So just looking at that, what exponent needs to go here, it would be a 3/4. So there's my answer there. And actually, that's a great segue to number 19. 19 wants you to take this fraction thing, kind of like we had here, and write it as a radical. So we know the a is going to be on the inside. Now it's just a matter of which one goes on the inside, which one goes on the outside. This is your root. The denominator is always your root, right? We said our 4th root, that's the bottom of our fraction. So we're going to have a cube root here. The 2 is really like my power. So this would be an a squared. And this is all it's looking for, is for you to do that. All right, I'm going to squeeze this last page in on this same video just because it's only a couple of problems and we're not too terribly long yet. Okay. So 20, write this without a radical. That's kind of asking you to do the reverse of what the last question was asking. If I were to put these back in, so without a radical just means write it as an exponent instead. And remember, these are your powers, and this would be your root number, which is the denominator of the fraction. So this would be like a to the power of 15 over 5, and then b to the power of 3 over 5. And then the only thing I would do there is if any of your fractions can reduce a little bit, I would. So 15 over 5 can really become a 3. 3 over 5 I can't do anything with, so I'm just going to write it as 3/5. And that'd be my answer. Okay, this next one is 3 different problems that you have to solve. And so I just want to remind you of a couple of things. One of them we already talked about is that if you can get an equation down to the point where it says log of something equals log of something else, you can take that and basically drop the logs off of there and just say, hey, these two things must be equal to each other. So that's going to happen sometimes. The other thing is, if you have log of something equals just a number on the other side, I would take this thing, and we'll put a base b on here, and spin this around to exponential form. So I would say b to the power of whatever that number happens to be equals whatever's in that box. And then you should be able to solve it from there. Now it'll depend on where your x is located, like how you solve it from there, but you should be able to solve it one way or another. Okay? And then the other thing we talked about, we've done a ton of these, but if you don't have any logs in your problem to begin with, but you've got a variable up in the exponent, you bring it down by taking a log on each side. So when I look at A here, just to kind of set my mindset up, I see that I have logs on both sides of the equation. So this is kind of what I'm shooting for. I want to get to a point where I have log of something equals log of something else and set these two things equal. In order to do that, I need to really combine what's going on over here. I need to get that down to a single logarithm. And because I see subtraction, I know that I can combine these with division. So I'm going to write this as log base 3 of 2x divided by 5 equals log base 3 of 12. Now I have myself in this position, right, where I have log of something equals log of something else. That allows me to just ditch the logs altogether. And now I can just say, hey, 2x over 5 is equal to 12. I know that this must equal this. To solve this, probably the easiest way to go would be to multiply by a reciprocal. So multiply by 5 over 2 to get the x by itself. And we're going to end up with, I'm sorry, I'm making a mess here at the end, but that should be x equals 30 when you do 12 times 5 over 2. Okay, so this next one, there's actually a real big shortcut that you could take with this one, but I hardly ever remember what the shortcut is. I usually have to at least think through it the long way first, so I'm anticipating that's going to be the same for you. I see a variable in the exponent, so I need to bring it down. Okay, and I know the exponent looks crazy right now, but if I need to bring that down, I'm going to do it with a log. And I don't have logs on either side yet, so I'm going to take a natural log. Again, I'm choosing a natural log because of that e there. And that's going to bring this crazy exponent down in front. So what I have now is this, ln of 5x times ln of e equals ln of 35. Now this thing looks like a mess, but the one nice thing that happens here is natural log of e disappears, right? Natural log of e is just 1. And so now what I have is natural log of 5x equals natural log of 35. I'm really in this boat again. Log equals log. So I can really just say 5x must be equal to 35. Which means my x value must be 7. And this last one, part C. Now you'll notice on this one, I have a log on one side, but not on the other. So now I'm in this boat. Now I'm in log of something equals a number. And so I'm going to solve this by doing a spin around here. I'm going to go 4 to the power of negative 3 equals x plus 5. So 4 to the power of negative 3, if I were to do that by hand, I would come up with a fraction answer. I think I'm just going to run with the decimal here. So 4 to the power of negative 3 is 0.15 or 0.15625. That's really 1 over 64 because 4 to the third power is 64 and the negative makes it so that it's division. So you could also think of it as a fraction, 1 over 64. But I now have this. I have 0.015625 equals that x plus 5. And then to solve for x, I'm just going to subtract 5 from it. So minus 5. And I end up with x being equal to, we'll just go negative 4.98. And that would be my answer. Okay, so that has been a crash course on Chapter 6. I hope that that has been helpful to you. After you've reviewed this, if there's any questions that are still kind of lingering out there, feel free to ask in class, and we'll go over anything that you need to. All right, hope you guys have a great